for d equal to 2, this becomes 1/4. So the probability that we go to any of these points is the same. It's symmetric and it's 1/4. And so a simple walk starting at this x, it can go anywhere, is a stochastic process. It is Sn. And if you start from x, then all of your increments, x1, at the second time we have another increment, at the nth time we have another increment. So it has a probability distribution. What is the probability distribution from x hitting y in n time steps? It's just the probability. So it's just, so by definition, instead of writing this, we always write this because it's easier to write. Now, the new process, these new processes are very important. Sn plus m minus Sm. So what is that? It means that your increment from time step m plus 1 plus increment from m plus n. And so we could observe that m plus n is equal to, we can first go to some states z, and then from z we can go to y. So we want to go from x and we want to hit y, so we can go to some intermediate states, z prime, so summation is over z, and then from there we can go to y. And that's why this relation holds. So a central limit theorem, I don't want to talk about local central limit theorem because it's a whole big theory for random walks, but we can say that we want to ask what is the behavior of Pn of x for when n is very big. And the central limit theorem says that Sn divided by square root of n converges to a normal random variable in Rd, which has a mean of 0 and covariance is I. And consider just an open ball in Rd. So we are not working on Zd, we are working on Rd. And imagine that the limit of this Sn, when n goes to infinity. Of course, there is another way to construct these interesting measures. For example, I'm interested in Fristlin ventil large deviation theory that is very interesting in diffusions, and that is another way of using ergodic theory. But now things are very easier, and this is just the integration over a of d over. So by central limit theorem, we know that it converges to that normal distribution. So for a set XA, we just sum over this this set. And now we can do a very interesting approximation. Instead of just a set, we say an atom, a singleton, I mean. In mathematics, we say atom. So this is equivalent to this. We can approximate this by n to the d over 2. So now you understand how this approximation originates from. It originates from central limit theorem, e to the minus d x to the t over 2n. And because mathematicians like to work easier, they try to weaken everything and use weak convergence, and that's the idea of characteristic functions. And characteristic functions, they usually use it for continuous random variables, because in discrete random variables we usually use generating functions, and I will talk about generating functions. And because I like the mathematician Abel for his work, and so these characteristic functions says that, for example, it talks about convergence of random variables. We have a sequence of random variables, and also it characterizes what kind of random variable it is. It's like a fingerprint, so that's why a characteristic function is so important. So it is just the expectation of I y theta. Think of it as just the Laplacian, and this is just summation over p y equal to y e to the I y dot theta, because this could be a vector, theta 1 up to theta d, and y is a vector as well, because y is in zd, so the inner product is just a scalar. So this is well defined. And the inversion of that, as I said, we want to go back to the original primal problem to see what happens. So what we do in mathematics, we go back, we do inversion. And the summation is on the set this, and the inversion is just minus I y theta, phi theta d theta. And the characteristic function of, this is very important, that the characteristic function of phi n for Sn can be calculated as, so phi n of theta, because they are identically independent, so one of them is enough, because we raise it to n. And phi of theta, if you look at the book of Lawler in 1996, Intersection of Random Walks, very interesting book, it is written that he has calculated this to be summation over cosine of theta j, and j from 1 to theta. And so Pn of x is just 2 pi to the minus d, minus Pnp to the d, always on this set, and e to the minus ix dot theta, phi to the n of theta, because we want to find the characteristics of Sn. And as I told you, it's just this time to the n, and d theta. And so I want to talk about proof of strong Markov property. There are many ways to talk about strong Markov property. One way is saying that, for example, we have A, and we start from here. And if you remember what I told you about the construction of that process, that new process that I told you, it was n plus tau minus s tau. So s tilde is equal to 0. S tilde 0. And then we go to s tau 1, which is x1. And then we go to s tilde 2, which is x2. And then we go out. And sometimes we go out of the set A. And the theorem of strong Markov property can be written like this. And we suppose that tau is just a stopping time with respect to filtration Gn. And then on this event, the process S tilde n that I've just told you is a simple random walk. You can observe that this is a simple random walk independent of your filtration, of this filtration. So we want to prove that this process, this beautiful process, is, for example, S tilde 1 is just S tau plus 1 minus S tau. S tilde 2 is just S tau plus 2 minus S tau. S tilde 3 is S tau plus 3 minus S tau. So it measures how close it is to your S tau. For example, here tau could be the first time that I exit. So S tau plus 1 could be here. S tau plus 2 could be here. And sometimes we come back and then we go out again. So we want to prove that this is a simple random walk. We let x0 and xn to be points of the lattice, and A is one of the members of the filtration up to time tau. And then the probability that S tilde is equal to x and S tilde n is equal to xn, intersection of that with that set that I told you, an intersection with the event that our stopping time is finite. So we can write this as saying that it is just summation over different combination of tau because it is finite. So it could be, so summation is over j, and it could be tau equal to j. It could be anything. And the same thing for A is the same thing. And here is the same thing, the probability. So this comes here. This is the same things. And now we can use, we can observe that this is equal to j from 0 to infinity. Instead of saying that Sj plus n minus Sj is xn and those things, we say that this is the same event. So we can say Sn equal to xn times, because it is independent of the that your stopping time is j. So we can write it as and after that this can come here, and the summation over tau equal to j could be written as just a intersection with tau less than infinity. And these things are very important because although I didn't talk about local central theorem, and in many proofs of theorems we just use strong Markov property. And using these interesting and important ideas, we can prove about the transience of a simple random walk. We can talk about recurrence of simple random walk. And this shows that understanding these two things and become an expert in using these two theorems are very important. Now I want to talk about harmonic functions Dirichlet problem again, but now we just work on ZD. our lattice ZD, and our J's component is EJ again, and so our functions becomes from ZD to R. And we call it the same idea, discrete Laplacian of f, but now it is we are working on ZD instead of general graphs. So delta f, the Laplacian, discrete Laplacian of f, is just I always understand Laplacian as a measure of the how close one function evaluated at one point is close to the mean value of f over neighbors of x. So it measures this discrepancy, how close it is. For example, 1 point, f of this 1 point, how close it is to the f at its neighbors. If it is the average, let's say, or mean value of f, then it is the Laplacian holds, and it satisfies the Laplacian. And another way to write Laplacian is just j from 1 to d, ej to f of x. But I prefer this one. So from the last page, we understand that we can write the Laplacian of f over the lattice as a difference between them, the expected difference of f of s1 and f of s0. And as I have told you several times, that harmonic functions are very related to martingales. For example, harmonic functions delta f of x equal to 0, it is related to martingales. For subharmonic functions, delta f of x is greater than 0. Subharmonic functions like a submartingales. Superharmonic delta f of x is less than 0. It's like supermartingales. And I want to prove a very interesting proposition that says if f is a bounded function, harmonic on A, and tau is the infimum of J, that Sj is not in A, then Mn is a martingale. And what is that? It is just S minimum tau is martingale with respect to your filtration Fn. And the proof is very simple. We write expectation of Mn plus 1, condition on your filtration, and let's see what happens. We know that we can write this Mn plus 1 I of Bn. And Bn, I mean just the event that tau is greater than n. So still our n is less than the stopping time. And plus expectation of Mn plus 1. So it is either n is less than tau or it is greater than tau. Bn complement condition on Fn. And we can write this as expectation of Sn plus 1 Ibn Fn. And we know that on the Bn complement, Mn plus 1 is just Mn. So we write expectation of Mn Ibn complement. And from here, this can go out, and let's evaluate the Laplacian for that, because we know that fSn plus 1